Hello students, my name is Shashank Shekhar. So we have started the chapter Electrochemistry. So today is our fourth class of Electrochemistry. So in the previous class, we have mainly discussed about what is the EMF of the cell and how we can use that Nernst equation to calculate the EMF of the cell. So if you remember yesterday's equation, the final general equation says that E is equals to, or you can say E cell is equals to E naught cell minus RT by NF ln Q. So this was our equation. Now, if you remember the terminologies, what are each of these symbols representing? So this was our electrode potential or EMF for which we are considering this equation. This is our standard EMF. The standard EMF means that all of the species that are taking part are having concentration of 1 m. This was our universal gas constant. It is temperature and it is number of electrons involved. First we have our Faraday constant whose value was 96500 coulomb per mole, and this is our reaction quotient. So this was our overall Nernst equation. Now today we will be seeing mainly the thermodynamic aspect of this Nernst equation first of all. Before that, starting that thermodynamic aspect, we will see a special type of cell. So in the previous class we have seen an electrode which was called standard hydrogen electrode, and we use that standard hydrogen electrode to calculate the electrode potential of any required species in which we are interested. Right. Now we will see a special type of cell in which we will have say both the electrodes dipped in the same compartment. So we will see this in the later slides. So if you look at the syllabus here right now, so we have covered up till this part. And today is mainly about the thermodynamic aspect and is specifically talking about Gibbs free energy change related to our equation and how it is related to the EMF of the cell. So this is our today's topic. So if you look at today's topic in more detailed manner, so firstly, before going to our thermodynamic aspect, we will see what are concentration cells and how we can calculate the EMF. This is very important. So children get confused in this concentration cells and they do make mistakes. After that, we will start our thermodynamic aspect starting from the Gibbs free energy relation with our EMF. And now we will use this to relate it with inotropy and enthalpy. So we will relate each of this thermodynamic parameter with EMF one by one. And they all will be in a chronicle order. After doing this, we will see the EMF calculation at equilibrium. So what happens to our EMF at equilibrium? And at last, we will see that how we can use this delta G value and why are we curious about the thermodynamic aspect of this EMF. So we will see this, right? So first of all, we will start with our concentration cells. So what are concentration cells? So concentration cells are those in which both the electrodes at different concentration are dipping in the same solution. Now how we will change the concentration of electrodes? Because I have said it earlier that we are taking metal as electrodes and metal concentration will be always 1 as metal are the pure elements. But in this case, the difference is that we are not using the metal for this kind of electrodes for changing the concentration. We use special electrodes like we have our say SHE or standard hydrogen electrode in which we can change the pressure to vary the concentration of hydrogen, because hydrogen cannot be taken in the form of electrode. So we take platinum as our electrode and we bubble the hydrogen gas through it. So I have discussed this thing in the previous class also. So what we are doing is we are taking that same standard hydrogen electrode, but not standard, sorry, but not standard, right? So we are taking hydrogen electrode only. And now what we are doing, we are dipping both this hydrogen electrode. So we are basically taking two hydrogen electrodes, and both these hydrogen electrodes are at different pressure. Say here we have P1 and P2. And what we are doing is that we are dipping both the hydrogen electrode in the same compartment, means in the same HCl solution. And then we are carrying out our say electrochemical cell, or you can say you are kind of preparing our galvanic cell. Now, why are we allowed to dip both the electrode in the same compartment? Because here we do not have two types of salt. We have only one type of salt, that is our HCl solution. So there is no risk of mixing two different type of salts, or having a displacement reaction or such. So we can keep both these electrodes in one compartment. If we talk about another example, we have our amalgam. What do? We take amalgam, and which amalgam? Lead amalgam, and we dip it in the lead sulfate. So what we are doing is we are taking lead amalgam in which lead are at different concentrations, say C1 and C2. So these are two concentration of lead, C1 and C2, and we are dipping it in the same solution, that is PbSO4 solution or lead sulfate solution. So here also the concentration of, say, our compartment is not changing, means the salt concentration is same. We are just, what we are changing, we are changing the electrode concentration by taking amalgam in this case, and in the previous case we are using platinum electrode along with hydrogen at different pressure. So this was our concentration cell. Now if I want to calculate its EMF, how will do it? So let us see the EMF calculation. So if I see the previous slide, you can see there that we have kind of this cell representation. We have P1 here. Okay. We have our P1 here. And we have this solution, HCl solution. And again, we have our hydrogen electrode, means the another hydrogen electrode with platinum, and we have a different pressure in that electrode, say P2. So it is ATM suppose, and this is also ATM. Now what we are doing is we are taking standard conditions. So the standard condition, not all the standard conditions, some of those, like we are keeping the temperature at 298 Kelvin first of all, and we are taking the gas constant in terms of joule per Kelvin per mole, that would be 8.314 joule per Kelvin per mole. So if you see this cell representation, you can see here very clearly that on the left hand side H2 is going to H plus. What is happening on the left hand side? H2 is going to H plus. So you can see here we have H2 at pressure 1, it is going to H plus, and we have, since we have two hydrogens here, so we'll have two hydrogens here also. So one hydrogen is losing one electron, so two hydrogen will lose two electrons, and we will get 2H plus plus 2 electron here. Again, if we go to the right hand side, we can see that those two electrons are taken up by this 2H plus, and again H2 is formed in the second electrode with a pressure P2. So we are doing both this reaction in the same compartment, so this concentration will be equal, this and this will be equal, so they all will be cancelled out. So this and this will get cancelled out, this and this will be cancelled out, since we are doing both the reactions in the same compartment, or we are dipping both the electrodes in the same compartment. So finally we'll get this equation in which H2 at pressure 1 is going to H2 at pressure P2. Right. So we have initially H2 at pressure P1 and it is going to H2 at pressure P2. Now the thing to notice here is that we are independent of concentration. So there is no concentration term in this equation, the final equation, and H2 can be considered as a final ideal gas. Now we can write the Nernst equation following our previous knowledge. So it was written like this. E cell is equals to E naught cell minus RT by NF. I have told you earlier also that RT by F is equals to 0.0591, in which R is taken as 8.314 and T is taken as 298 Kelvin. So if you put all these values, and Faraday was 96500. So if you keep all these values, you will get it as 0.0591. Now since we can see here that we are involving two electrons in each of these equations. So if you see both these equations, we are having two electrons. How much electrons? Two electrons. So it will be E cell is equals to E naught minus 0.059 by 2 log P2 by P1. Why P2 by P1? Because we have P2 as on the product side, means the hydrogen which is having pressure P2 is on the right hand side. Similarly, P1 is on the left hand side, means the hydrogen that is carrying that charge, it is on the left hand side. So overall it will be product by reactant, that is P2 by P1, and it is also at 25 degrees Celsius. So it is mentioned here. Why? Because if we change this, we will get an alter value of this 0.0591. So this is our EMF calculation of concentration cells. Next, we will move to thermodynamic aspect of this electrochemistry. So we will see the thermodynamic aspect. So we'll start with this Gibbs free energy. So this equation is very popular. So if you have studied the thermochemistry or the electrochemistry, you must have seen this equation. So what does this equation signifies? That the change of the Gibbs free energy is equals to minus n times Fe, where n is the number of electrons involved in the reaction, F is as usual our Faraday's constant, and E is our EMF of the cell. So this is our very important equation. Now, if we have concentration, say all the concentration is taken as unity, means all the salt we are considering as unity. So basically I am trying to invoke the say concept of standard electrode potential. So we are taking a unity concentration of the reacting species. Then in that case we will say that E cell will be equals to E naught cell. E cell will be equals to E naught cell. So delta G naught will be equals to minus NFE naught, minus NFE naught cell. E naught is our standard electrode potential. Standard electrode potential. Now this equation is also very important. Okay, so this equation plus this equation, both are very important equation after our Nernst equation. So this is our thermodynamic relation of Gibbs free energy with EMF. Now we'll explore this more and more. Next, we have this inotropy and EMF relation. For this, you must have studied this, say, thermodynamic. If you have not studied, it's okay. We can just remember the final equation. The final equation is of more importance rather than the whole derivation. So if we see this equation, this is the relation of inotropy change with EMF change. Okay. So this is equation says that the net inotropy change is equals to N times F times the change in EMF with respect to temperature at constant pressure. Now, you may ask that what's the significance of this equation? Why are we using this type of D and not the normal D for differentiation? So there is a difference between this D and this D. For those who are from the say mathematics background must have seen this. So this is our partial differentiation. Partial differentiation. And this is complete differentiation. So when we solve question, we will see the difference between these two, right? So what is happening here is we are differentiating the E naught with respect to temperature at constant pressure, and we are multiplying it by NF, and we are getting our delta S naught, or our entropy change. Now, if you want to see a derivation, it is quite simple if you are aware about our Maxwell equation. Our Maxwell equation. So, Maxwell equation says that delta G is equals to delta dP minus SDT. So, this equation is well known. Now, what we have done is we have taken the pressure constant. What we have taken? We have taken the pressure constant. So, this equation will become delta G is equals to minus SDT. No problem. Now we have just differentiated with respect to dt on both sides, and we got this. Oh, one more thing. Do not assume it like this, that I have transferred it here. Okay, so it is not in that way. Yeah, it will result in the same equation, but it is wrong to say it like this. Why? Because it is differentiation. It is a function, not a number. You can just cross multiply it and get your required answer. So what we are doing here, we are just differentiating both sides with, again, with respect to delta G. So it is like this. You will follow the same rule as you were following in solving your inequalities. So if you just differentiate delta T on both sides, this will be followed further. So at constant pressure we are differentiating, because we have assumed that we are having constant pressure, and this will move to 1. You know this very well. So change of temperature with respect to temperature. So they both are the same thing. So their relativity will be always equals to unity. Now finally we will get our equation as S is equals to minus delta G by delta T at constant pressure. So those who have studied thermodynamics minutely must have seen that whenever we calculate any thermodynamic property, we do not calculate the absolute value of it, because it is impossible to calculate the absolute value. So rather than calculating the absolute value, we are always interested in calculating the change in entropy or change in any thermodynamic property. So here also what we will take the change. So we know what is change. The change is very simple. It is delta. So delta S is equals to minus this partial differentiation of delta G with respect to temperature at constant pressure. So basically what I have done is we have taken a delta S. So it will result in delta G only. Now temperature can be done. Means this temperature differentiation can be found out. But this Gibbs free energy differentiation, it is impossible to calculate the change in Gibbs free energy without say in the small amount of time. So by which I mean that it was initially written this G. Now this is a very small limit. You cannot calculate Gibbs free energy at these two small instances. Rather than we take a greater instance. So finally you have to remember this equation. Now we know from the previous slide that delta G is equals to minus NFE. So I have put this value here. Now this NN, E and F, 3 are there. Out of these 3, this is constant and this is constant. So this E will remain inside the differentiation, and all of the remaining N and F will come here. And we will get this equation lastly. So this is our resulted equation, or the important equation. So we can just proceed with this equation further and calculate the enthalpy also with the help of this equation. How? So we know this thing, that delta G naught is equals to minus NFE. Again, this will be delta. This will be delta G by delta T, and this will also be delta. We know this thing. So we have just written it for standard condition. Now we got the final equation, this one. So if you remember this equation, delta H is equals to delta G plus T delta S naught. So we know that delta G naught is equals to minus NFE naught, and delta S, we have calculated it right now. It was say delta E naught by delta T into NF. So finally we got this equation. So this equation is also very important for examination point of view. So we are not using any rocket science here. We are just implying the thermodynamic concept here and calculating our enthalpy change, Gibbs energy change, and entropy change. So all this thermodynamic property are calculated using our simple thermodynamic relations. So we will consider equilibrium now. So far we have seen the Nernst equation. Now we'll consider the what happens at equilibrium. So to start with equilibrium, we will start with this delta G is equals to minus NFSL again. And at equilibrium, we know that delta G value is equals to 0. Right? So if delta G is equals to 0, so if this is 0, so this E cell will be also 0. Okay? This E cell will be also 0. Now next, Q will be equals to K. Okay, Q will be equals to K. I think this will be K. And so if we put this, all these values in Nernst equation, we put all these values in Nernst equation, and we got our E naught cell as RT by NF ln K. So this is our final equation, which says that at equilibrium we have E naught cell is equals to RT by NF ln K. Okay, so in this way we can calculate our Gibbs free energy change, and we can use this Gibbs free energy change to calculate entropy and enthalpy. Later on at equilibrium we can calculate E naught cell using our equilibrium constant only. Now the last topic of today's class is calculation of the EMF and delta G naught for the cell equation. So basically what we are doing is we are using this delta G and using it to calculate our E, your EMF of the cell. So why we are not doing it directly? So you will see what is meant by directly here. So if you see, we have to find the EMF for this equation and delta G for this equation. And we are given with these values. Okay, we are given with these two values. So these are the reduction potential of zinc and cadmium. But if you see this equation, cadmium is getting reduced. Okay, good. But zinc is getting oxidized, not reduced. So what do we need here? The oxidation potential of zinc. So what it will be? It will be just opposite. Main thing, we will just change the sign. So this will be our oxidation potential for this couple. Okay. Now, this thing is given here. So if you want to write the equation, so you must write the equation, because writing equation is a good practice to do. Okay, so you will write the equation for this and for this. But the overall cell reaction is this one. Why? Because cadmium 2 plus is going to cadmium and zinc is going to zinc 2 plus. So this is our final equation. So what will be the EMF of the cell? So it will be E naught cell will be equals to this one. So I have told you earlier that if oxidation potential is given and you have to get the reduction potential, you will just take the opposite sign. And if your reduction potential is given and you have to find the oxidation potential, you will just take the opposite sign similarly. So here we have the reduction potential of this, but we do not have the oxidation potential of this couple. So we have just inverted the sign and got this oxidation potential. Now we'll add this and this. So it will be simply 0.763. Addition of this with this will give you minus 0.403 is equals to 0.360 volt. So you got your equation, right? Which is 0.360 volts. It is our E naught cell. Now, if you want to calculate the delta G naught, how will calculate? So you have seen that 2 electrons are involved in both the equations. So number of electrons is 2. Now what is the Faraday constant? We know it very well. It is 96485 So do not get confused here. So sometimes you must see this 96500 coulomb, and sometimes you will see this 96485. So both are correct. Accordingly, we use means what is the question saying, that in that way we will use. Or if in the start of the question only you are given the values, then well and good. Okay. So what we have done, we have put these values and we got our delta G naught. So this is our final delta G naught value. Now I want to give you an illustration here. One more illustration which will help you to think in a way about the calculation of EMF if you are given two different cells, and you are told to combine both the equations of the cell and get your third or a different cell EMF value. So first of all, you cannot add the EMF value. It is not possible to do so because EMF is a intensive property. So if you have studied thermodynamics, you have seen that two type of properties are available. The first one is intensive property and the second one is extensive property. So if we said that if you have intensive property, it means that we are having, say, we are having the property which is only dependent upon the nature and not upon the number of particles. So intensive property is one which does not depend upon the number of moles, number of molecules, or number of atoms. It does not depend upon the amount, whereas extensive depends upon the amount. Now, if you talk about the properties of this intensive property, then the first one is that it is not additive in nature. So if you know the intensive property of 2, and the third one of which intensive property you are looking for is the simply sum of the previous two, then you do not need to do the sum, or you cannot do the sum. So it is not standardized to do the sum. You will get your wrong answer wrong. So what we will do in that case, so we'll calculate something which is additive in nature. So I want to make a point from thermodynamics that Gibbs free energy is an extensive property, and I should have mentioned this earlier also, but I am mentioning it right now, that EMF of a cell is an intensive property. So it is not additive in nature, but Gibbs free energy is additive in nature. So we will take the benefit of this additive nature of Gibbs free energy and plus our formula delta G is equals to minus NFE to calculate our EMF. Now let us illustrate with the help of an example. Suppose you're given an equation like this: Cu2 plus and 2Ag plus, it is going to Cu and 2Ag plus, like this. And another equation which is given is that Ag plus, and suppose we have taken another example, say we have this Zn, which is going to, I'm just taking a hypothetical situation, we cannot say that it is the only way to do so. Sorry, it is not the only thing that is written is right. So it will become Zn plus, suppose, and it is becoming Ag plus, sorry, Ag at the last. And you are given the E cell of for both of this. Sorry, or say the E naught cell for both of this. Suppose this is X, this is Y. X volt and Y volt. Now you have said that okay, found out for this equation, which is this one. Now, from thermochemistry, you have seen that if it was about the thermodynamic property like enthalpy, or say we have this Gibbs energy or entropy, then what we would have we done? Then we have just would have been simply added these two equations, get this thing cancelled out, or if firstly we multiply it by 2. Yes, we have multiplied it by 2, and these things will get cancelled out easily, and the final EMF would be, means the E naught cell would have been X plus Y naught. But it is wrong. It is totally wrong. We cannot do this thing. Why? Because right now I have told you that this is not additive in nature, or the EMF cell is not additive in nature. So what we will do? So the thing we'll do here is that we will calculate the Gibbs free energy for each of these three. And then with the help of these, we will find the EMF. So how we'll do it? So suppose this is our E naught cell. So what will be the del G for this? So del G will be equals to, so if you are talking about the first cell, so suppose this is the first cell and this is our second cell. So if you are writing for the first cell, it will be minus N F, and E naught is given as X. What is the value of N here? It is 2. Similarly, we will write delta G naught for second, and it would be minus 2Fy again. So this is the thing. Now we have to calculate it for the third reaction. Suppose this is our third reaction, third cell. Now I have told you right now that this Gibbs free energy change is additive in nature. So we can get the third cell by simply adding these two. So what we will get? We will get it as delta G naught for third is equals to minus 2 Fx plus minus 2 Fy. This is our Gibbs free energy change. Now if you consider this equation, if you are have to write delta G naught for this, it would be minus 2 Fe. So this is our Gibbs energy change, and this is also our Gibbs energy change. Equation 1 and equation 2. Now we'll just equate both of this. So it would be minus 2Fe is equals to minus 2Fx plus, or sorry, 2Fy. So if we'll add this minus will get cancelled out. F will get cancelled out. And we will get E is equals to X plus Y. So you may be getting confused that, sir, you have told that in the early times that you cannot just simply add this, but at last you have done this only. You have simply added this. But believe me, in some cases, so I will show you some questions also. So if you do this directly, you will end up doing the sum wrongly. Because in some cases, what will happen, the number of electrons involved, since there are two in each of these three, so it has been cancelled out easily. But in some cases, it will not happen in that way. Okay, so it will not happen in that way, and you will get up doing it wrong. So for this, what you should do, you should follow this algorithm. So first you will find delta G for this. Again, we will find delta G for this. You will calculate your delta G. Then you will find the delta G for this in terms of E. Then you will equate both of these equations, and finally you can get the value of E. Right. So this was our EMF calculation using delta G. So if I put whole of this thing in a nutshell, so let me write it for you. So we have gotten too many formulas. So the first one we have studied is the Nernst equation, which says that E cell is equals to E naught cell minus RT by NF ln Q. Now if T is equals to 298 Kelvin and we are taking standard condition, then this RT by F will be equals to 0.0591. So this was our first equation that we have seen. Now moving on, we have seen the thermodynamic aspect starting with Gibbs free energy, which says that delta G naught is equals to, or delta G is equals to minus NFE naught. So this is also a very important equation, right? Then we have connected it with delta entropy, which says that since we have this equation as dg is equals to minus P dV minus S dt. We have this equation. Yes, at constant pressure. So it was at constant pressure. Now if you differentiate it, you will get it as delta G by delta T. At constant pressure, we will get it as minus S. Now what we have done, we have taken the change and it resulted in this equation. Okay. Now delta G is equals to minus NFE. That would give us delta G E. Delta G is replaced by E by delta T is equals to minus delta S. So minus minus will get cancelled, and this is our final equation. That delta S is equals to N F delta E by delta T at constant pressure. So this should be mentioned at constant pressure. Further, what we have done, we have taken this equation which says that delta G is equal to delta H minus T delta S. So if you want to calculate delta H, it would be delta G plus T delta S. We know the value of each of these. Delta G is equals to minus NFE. Suppose we are taking standard condition. So it would give us minus NFE naught. Minus, then T delta is equals to this thing, NF delta E by delta T at constant pressure. Okay. So in this way, we can find our delta H naught. This was our another equation that we had. Then we have moved to equilibrium. At equilibrium, we have said that the value of E cell is equals to 0 and Q is converted to K. Therefore, we have written that E naught cell is equals to RT by NF. Then we have this ln K. So these were all equations that we studied today. So you must remember all these equations. These equations are important. If you do not remember the formula, it's okay. But sometimes maybe you're asked the question in a way that you need to derive the formula accordingly and get your final formula, and then you can get your calculation. So if it is possible, just remember the formula. That will be good for you. Then if I talk about tomorrow's class, so we have covered this Nernst equation part. So it is just a part of electrochemistry we have covered. So basically the second part may be basically about conductance and all. So we'll see what is conductance and how this electrolytic conductance work, what is weak electrolyte, strong electrolyte, and all those. The most important thing that we'll see is the Kohlraasch law. So thank you for today's class. So with this, I end my lecture.